Let's take a look at the next section. So this should be 9H in differentiation. It talks about implicit differentiation. So this is something that'll be quite new to you. We've looked at rules so far, lots of rules: chain rule, product rule, quotient rule. Implicit differentiation is sort of an idea to the side of that, okay? So you might have a question that has product rule and chain rule or something. You can still have implicit differentiation as well, okay? So you need to be prepared that this can sort of come up when you don't expect it. And it tells us how to deal with situations like this. So if we wanted to differentiate this, that might be a bit of a problem for us, because so far we've been differentiating things in the form y equals, don't we? Like y is some function of x. In other words, y is on the left and lots of x's on the right. That's what we've had so far mainly. But what about this one, or this one here? In this one, you could have y appearing multiple times. And again, it's not obvious how to deal with that. So the thing we're going to do is we're going to talk about how we differentiate y, if you like, when we're doing this differentiating of x. And you have been doing it all along, but we haven't really made it explicit. So, for example, when you had y equals x squared, you have known that you've been differentiating the x's, right? So x squared became 2x, nothing new there. Well, on the left-hand side, you just took it for a given that we said dy dx. But what you were actually doing is you were differentiating the left-hand side with respect to y. In other words, you differentiated y to 1, and at the same time, you were differentiating the right-hand side with respect to x. But that doesn't really work. We don't really like that, okay? Because we're meant to do the same on both sides really when we differentiate. But the trick is, this one here is what happens when you differentiate with respect to y. That's the 1, okay? And then next to it, we write dy dx. Again, this is the dy dx that you've seen before. If you remember what we talked about in parametric differentiation, we talked about a chain rule. Well, actually, you've been doing a chain there. So indirectly, you were differentiating with respect to x, where the bit on the left, the y itself, the differentiating of the y was 1, and then you wrote a dy dx next to it. It's just that you couldn't really see this. So don't worry, I'm going to give you some more examples to illustrate the idea. So we talked about differentiating y. If you were to differentiate with respect to x, you would get dy dx. But really, that was 1 times dy dx. Well, what about what about y squared? So the basic idea is this: differentiate this exactly as you want to. So in your head, you want to say 2y. That's fine. You're differentiating there the y. But if you do that, and you have been told and you've been given the instruction to differentiate with respect to x, next to that, you must also write dy dx. And then indirectly, you have differentiated with respect to x. So this part here is the 2y, but you must write your dy dx. So y squared differentiated with respect to x, that is the answer. So it's 2y dy dx. If you like, you can think of it as differentiate the thing as you want and put a dy dx on the end, okay? That way of viewing things tends to work pretty well, in all honesty. So sine y, differentiate it exactly as you want to. You want to say cos y. That's fine, but because it was y and you were differentiating with respect to x, you should put a dy dx on the end, okay? Just before I talk about the rest of them here on the screen, I want you to have a think about what you would do. So the essential idea is differentiate as you would want to, but if at any point you are differentiating y's or functions of y, you must have that dy dx on the end to create a chain rule. So ey is ey, but with dy dx. What about this one here? Well, that is a product, isn't it? That's a product. So you use the product rule. Okay, so you would write u equals x, du equals 1. Why have I done that? Well, just as normally, yeah, x differentiates to 1. V, the other part, is y. Well, how do you differentiate that? 1 dy dx is the answer, okay? It's not just 1, because the question is differentiate with respect to x, and I have a y, so I need this dy dx. You can get rid of the 1 if you want, okay? And then you put things together. So u dv will be x dy dx plus v du is going to be y. Okay, that will be your answer. Very common to have this and be asked to differentiate this. This one here, a bit more complicated. So think of e to the bracket. So if you differentiate e to the bracket, you get e to the bracket multiplied by what is inside the bracket differentiated, which is also a product. It's quite a difficult example, really, to get started with the idea, but you should be able to get this result. Okay. What you do, you just have the bracket again. Okay, so you would have ex squared y. This bit here differentiated, you need to kind of go off to the side of your paper and do this again. Okay, and you will get that result. Same thing here. So this is a chain rule, isn't it? There's x plus y inside the function, and then there's tan itself. So tan becomes sec squared of x plus y. But you also have to multiply it by inside differentiated. X becomes 1 and y becomes dy dx. So yeah, look, they've written it that way there. So they put the 1 plus dy dx at the front. X squared plus, well, the x squared is a nice part. This part here you have to watch out for. So minus sine y, sure, but you're differentiating with respect to x, so you need that dy dx. So all the x parts, differentiate as you normally would, use the rules like you normally would. But if, as you're working out the pieces, or if you're just using results, if at any point you find yourself differentiating a y when you've been told to do it with respect to x, you need to add the dy dx on the end. Let's do some exam questions. This is a pretty accurate example, I would say. Find dy dx. Well, that's telling you then, isn't it, that you need to differentiate with respect to x. So x cubed will become 3x squared. X will become 1. So there's some easy differentiation in there thrown in amongst the harder stuff. Y cubed, you want to say 3y squared. So that's fine, but you need the dy dx because this is implicit differentiation. And 3y becomes 3, but another dy dx. Do not forget the 6 becomes a 0. Okay, so notice how dy dx can appear more than once in a question. That's quite a new idea. Move the non-dy dx parts to the other side. So I'm going to say 3y squared dy dx plus 3 dy dx equals minus 3x squared minus 1. If the thing appears twice and you only want it once, you need to factorize to take the dy dx out. So dy dx of 3y squared plus 3 equals minus 3x squared minus 1. And then you move this part underneath. So your final answer will be dy dx equals minus 3x squared minus 1 all over 3y squared plus 3. Okay. Just check. Yeah, that's what it wanted in terms of x and y. So we've done that. This one here is the same question, but they give you a coordinate and they want you to find the value. So we're going to do the same thing again, but then we're going to actually use the answer. Notice how x and y are often both needed for the gradient. So it's not just like you can just use the x. Here, you probably need the x and the y as well. So what have we got? It looks a little bit complicated, this one here. That looks like a product rule to me. So there's some function sat next to another function. So u equals e to the 2x. V equals natural log of y. The right-hand side looks like it's not too bad. So du should be equal to 2e to the 2x. That's the chain rule, although you might remember it as a special result. This is 1 over y, but you've been differentiating y's here, when it was all about differentiating with respect to x. So you need that part there. crisscross. So u dv for the product rule. So what's the easiest way of writing this? E to the 2x over y dy dx plus what's the other one? You normally put the powers at the front. So let's do 2e to the 2x natural log of y. That's the left-hand side, okay? So I've done the left-hand side there now with the product rule. Don't forget the right-hand side. X becomes 1, y becomes 1 dy dx, or just dy dx if you like. And the minus 2 is gone. So quite a lot of stuff there, yeah? And we need to find the value at 1, 1. So I'm probably not going to have enough space. I do a little bit. You would need to rearrange this now, okay, to get dy dx to only appear once in a similar kind of way, so a fair bit of manipulation, and then you would put in x equals 1, y equals 1 to get a value. That's how you would finish this question, okay? I'm just thinking if it might even be easier for this question here if I substituted the values in straight away. I think I'm going to do that actually. So if I put in x as 1, that will become e squared. Y is 1, so over 1. So that part there is done. Whoops, that part there is done if I put a dy dx there. 2e to the 2x, well, x is 1, so that's going to be plus 2 e2 times natural log of 1. Natural log of 1 is 0, so that whole term there is going to disappear. Equals 1 plus dy dx. Do you see that saved quite a lot of time? Because it says find the value. I could have manipulated it like I did here, but that saves a lot of time for that question. Get the dy dx's on both sides. So let's say e squared dy dx minus, bring that one over, dy dx equals 1. Factorize the dy dx out. There's no way to get around that. E squared minus 1. And there we go. 1 over e squared minus 1 should be the answer. Okay, so depending on what the question wants, if you think ahead, you might be able to save yourself a little bit of work. Let's just see if we've got neater versions of those ones there. Yeah. Okay, so they've done the same. Substituting sooner rather than later is a good way to go here. Pause the video then and have a quick go at these ones here. I would say these are very representative of the new spec as well. Something like this. It's probably not as broken down as these questions are. So pause the video and have a go at these ones here. Okay, so find the coordinates of the 2 points where x equals minus 8. So don't get too carried away. Finding coordinates is about using the original, isn't it? Okay, there's actually no differentiation there at all. That's just about putting numbers in and finding out some coordinates. Maybe it's related to later on in the question. Find the gradient. Gradient, that means you need to differentiate. Find the gradient at each of these points. So you know these points, you're going to differentiate, so you've got something to put those numbers into. That's what's going to happen. So implicitly, you get all of this stuff here, okay? And then you put your numbers in once, and you see what you get. You should get minus 3, and you put your numbers in again, and you get 0. You can get a lot of marks on implicit differentiation fairly quickly, but you need to be really, really accurate and really methodical with it. The other one, so find dy dx straight away. So like we said, some nice differentiation, some common patterns that you will spot there, some nice differentiation, some fairly nice as well. And there's the xy again, okay? So that's the one you need to just spend a little bit of time on the xy, okay? So you go off to the side and you say, well, my u piece is 4x, my v piece is y, that's dy dx, yeah. Your du bit is 4. You spend a little bit of time, you'll get quicker and quicker at it as well. So look, 4y, 4x, dy dx. You can see where that's coming from. You get lots of dy dx's. You've got to try and collect them together and factorize out. And when you get to dy dx equals this, fully simplifying your answer. So fully simplifying here, that's about the fact that, look, even. You can divide numerator and denominator by 2. Find the values when dy dx equals 0. So when is that fraction equal to 0? Have a think about that for a second. When can you get a fraction where the answer is 0? There's only one way you can do that. The numerator must be equal to 0. We're not going to talk about the denominator at all, because that will give you a maths error, or you will be talking about infinity or something like that. Okay. The way to achieve this here, when you have a fraction, is to make the top part equal to 0, which simplifies things quite nicely. So in other words, the top line is x plus 5 minus 2y equals 0. That's what you would need to work with. Okay, so there's that. We get this equation. You think, okay, but how am I actually getting answers? Well, this is an equation about x and y. And there is another equation about x and y. So they're both about coordinates of these here, so you can solve them together simultaneously. That's an interesting twist about how that question's gone there. A little bit difficult. Something to note, though, this one will come up a lot. Okay, that piece of understanding there is really, really important. And it doesn't get explicitly talked about in the textbook an awful lot, apart from this point here, really. Okay, so that takes you to 9H. So spend some time on implicit differentiation, because this is a topic that you can expect to see come up at least once in a paper. And like I said, it's worth quite a few marks.